This video will provide an example of how to create a layered tissue model from an MRI scan. aevaSlicer version 2.3 is used for the beginning of the tutorial, but later updated to version 2.6. Bone and muscle will be individually segmented, and the fat and skin will be lumped into one segment. The input for the model is an MRI scan. The output will be an FEBio model file. There are a variety of methods to segment the tissues. More detailed videos on segmentation methods can be found on this channel. First, to segment the bone, using the grow cut method is appropriate given the contrast between the bone and the muscle boundaries. Using the paint tool, color in a few slices in each direction of the femur. Then create another segment and paint closed boundaries around the femur to isolate its background. Choose Grow Cut and Initialize to preview, and make sure that the boundaries of the bone are captured. A more detailed description of this Grow Cut method can be found in the aevaSlicer playlist. Next, to segment the muscle, an appropriate method in this case is level tracing. As boundaries are irregular and challenging to define in some areas, level tracing identifies where pixels have the same background value as the current background pixel, or one that the cursor is pointed to. After several slices are segmented in each direction, the fill between slices operation can be used to fill in the rest. The first and last slices should be segmented along the direction of the bone. Using the preview is helpful to decide if more segmentations are needed before filling. You can see that it also included area in the bone that we don't want for the muscle segmentation. The Logical Operators tool is a suitable option to erase unwanted area that was captured in the bone. It can be used to add or subtract different sections based on the condition selected. In this case, the bone is subtracted from the muscle segment. Next, to segment the last layer of the tissue model, the Logical Operators tool can capture the skin and fat layer as one. This area would be time-consuming and tricky to segment manually like the muscle. A hack to segment the skin and fat is to fill in the black background of the MRI based on its pixel value, and then use the fill option to define the rest of the area as skin and fat. Add a new segment and make sure the editable area is outside all visible segments. Adjust the editable intensity range so that it is set to the value of the background. After applying these parameters, the new background segment appears. The only area left is what will be the skin and fat segment. Add another new segment and choose the fill operation while keeping the editable area outside of all visible segments. Apply this configuration and rename the new skin fat segment. The background can then be deleted. Joint smoothing is used in this case to clean up the segmentation borders and so that they do not overlap. Some manual cleaning with the eraser tool is useful to remove any unwanted area captured from the segmentation. Next, surfaces are generated at the Surface Meshing tab. The input is segmentations that contain all labels. The Smooth Models tab adjusts the amount of smoothing applied to the output meshed surface. Once the meshes are created, the density for each component can be adjusted. Use the bone surface as the input and a new output model for the output. For example, the bone is remeshed at a maximum global element size of 1. The status bar at the bottom left will confirm when the remeshing is completed and can be seen by hiding other components and switching the view to surface with edges. The bone can be remeshed again to a denser mesh by changing the maximum global element size to 0.5. The remeshing process may take longer to create a denser mesh. Multiple densities can be created for each model component and saved individually. Next, with the resulting surface generation, volume meshes can be created in the next tab. Each surface mesh is used as an input to generate a volumetric mesh. The TetGen module will be used in this case to create a volume mesh with tetrahedral elements. Once the 3 components of the model each have a volume mesh, we can move on to aeva's computational model builder, or better known as aevaCMB. Before moving on, all of the files and information in this scene can be saved in a .mr, ml, or MRML file, which stands for Medical Reality Markup Language. By choosing File and then Save, the first option in the window is the MRML file. Accept the prompts to save, and after closing the scene, I can reopen it quickly by just opening the MRML file to bring back all of the volumes, meshes, and labels. Another way to save this scene is a Simulation Modeling Toolkit file, or SMTK for short. Software version 2.6 or later is needed to save as an SMTK file. Choose Save, and from the drop-down, change the MRML file format to SMTK instead. Now this SMTK file will carry all the files over to aevaCMB to further build the model. Moving over to aevaCMB in the SMTK file we just saved, it loads all of the files into a resource. The components can be expanded to show or hide its contents. For the last part of this tutorial, we can look at how to define surfaces and nodes at interfaces. For demonstration purposes, I'll define a surface by proximity from the bone to the muscle layer. Choose the bone surface from the right panel that contains the files. Double-click it and look to the Operations window to find the proximity feature, and double-click to bring up its options. Choose the muscle surface as the target, and in this case, as it is just for demonstration, we can arbitrarily choose a distance of 1. Apply and make a copy of the selection, and it will show up in the resource tree. The surface can be transformed into nodes that define an interface for the model by choosing the points on the surface that was just defined. At the top right of the window, while the new surface interface is selected, choose the second orange box icon to select the nodes of the primitive selection. Make another copy of this selection to make it appear in the resource tree. Finally, this model can be exported to an aevaBio input file that includes all components of the model and new groups created. Select the resource and double-click the Export FEB option. Simply choose a location to save the aevaBio file and apply. Try to open the exported aevaBio file in an XML editor and view the groups of nodes and elements that make up the model. Check back on this channel for a more detailed look at some of the features used.